Hello and welcome to the video lecture on Fourier series. In this video lecture, we shall see some of the examples on full range Fourier series expansion of the function. So let's start with the first example. Find the Fourier series for the function f of x is equal to pi minus x whole square by 4 over the interval 0 to 2 pi. So see here, in the earlier video lecture I have told you how to select the proper formula of the Fourier series expansion. So this is nothing but a simple question of Fourier series expansion. So whatever interval given over here is nothing but a interval of the length 2L, where here L is nothing but pi. So we will apply accordingly the formula. So given f of x is pi minus x whole square by 4. So therefore it will contain all the coefficients, that is a0, an and bn. Hence the Fourier series of f of x is given by f of x is equal to a0 by 2 plus summation over n equal to 1 to infinity of an cos nx plus bn sin nx, where we need to find out these three Fourier coefficients, that is a0, an and bn. So let's find these three coefficients. So a0 is given by 1 by pi, as this being a full range expansion, that's why over here the formula will be 1 by L. L is here pi. So it is 1 by L, and whatever limits are given that will put in the integral, that is from 0 to 2 pi of f of x dx. Now f of x over this interval is given as pi minus x whole square by 4. So that will substitute over here. Now integrating this, so integration of pi minus x whole square is nothing but pi minus x whole cube. We will use the formula ax plus b to the power n, right? Integration of ax plus b to the power n. So that gives you this pi minus x whole cube upon 3, and then derivative of pi minus x, that is what? Minus 1. So we have expand the integration of this as pi minus x whole cube by minus 3. 4 being a constant, we will take it outside. Now integration is done, so we will apply the limits, that is 0 to 2 pi over here. And on simplification, you will find the value of a0 as pi square by 6. Okay, now let's have the next coefficient, that is an, given by 1 by pi. What is the change over here? As this is a Fourier coefficients, right? For the cosine term, so that's why over here in this formula we will just make one slight change, that here instead of f of x only we will have cos nx also in addition in the multiplication with f of x. So we will have 1 by pi integral 0 to 2 pi f of x cos nx dx. Again substituting f of x. Now you can find here this in the form product of two function, where one is the algebraic term and another is a trigonometric term. So in this case we will apply integration by parts, or as here we have advantage that one of the term is algebraic term, this term is algebraic. Okay, so we can apply the successive integration by parts also, that is Bernoulli's formula, which I have mentioned in my previous video lecture. You can go through it, how to use the Bernoulli formula, that is successive integration by parts. So let's use this. So this is my u, that is the first function, and this is a second function. So we will take out the constant outside, that is 4. Now first function is pi minus x whole square. Okay, then integration of cos nx, that is second function, is sin nx by n, right? We will write each term inside the bracket, so that it will become easier for us to identify which one is the first term entirely and a second term. So this term inside the bracket is the second term, whereas this is nothing but a first term. Okay, now then we have minus sign, then minus, after that we will have the derivative of previous first term. This is the previous first term, so we will differentiate that. So what we find, its derivative is 2 times pi minus x, and again derivative of pi minus x will be minus 1. So that's why minus 2. Then integration of previous second term, integration of previous second term will be what it will be. So integration of sin nx is nothing but minus cos nx upon n, and n is already there, that's why n square. Then we will write next term. So here we will find in successive integration by parts we have alternate plus minus sum. So plus sign, then minus sign, now it comes plus. Then derivative again of the latest previous first term. So this is the latest previous first term. So we will take the derivative of this, that comes out to be what? It comes out to be 2. Okay, and then integration of this one. So what you will find? So you will find the integration of this is minus sine nx upon n cube. In this way the integration is over. Now let's apply the limit. So accordingly we will apply the limit, upper limit as well as lower limit. So what we find that we will have such type of terms after substituting the limits. Now here cos 2n pi is nothing but what? It is minus 1 raised to power 2n, and minus 1 raised to power 2n becomes the even integer, right? Why? Because n takes the value 1, 2, 3. So 2n will be 2, 4, 6. So cos of 2n pi will be nothing but plus 1. Okay. Then we need the value of cos 0. Cos 0 is also 1. Okay. So accordingly substituting the values of these. So and after simplification you will find the value of an as 1 by n square. So now we have obtained the second Fourier coefficient. Let's have the third Fourier coefficient, that is bn. So it is 1 by pi. Now this is multiplication coefficient for a sine term. So that's why in integrand we will find in product with f of x sine also, right? So it is sine nx. Again substituting f of x, simplifying it in the same manner, right? So we will again apply successive integration by parts over here. So first term, then integration of second term, minus derivative of previous first term, then again integration of previous second terms. Likewise we will do the integration and then we will substitute the limits. Again we will have to make use of the formula, that is cos 2n pi. Remember cos 2n pi is 1. Okay, cos 0 is also 1. So substituting corresponding values you will find that all terms will get cancelled and you will have bn as 0. So in this way, after getting the values of a0, an and bn, we will substitute all values in formula 1, that is nothing but this equation 1, right? So substituting the values over here, a0 as pi square by 6, then an as 1 by n square and bn as 0. What we get? So f of x. What is our f of x? It is pi minus x whole square by 4 equal to a0 is pi square by 6 upon 2. So that comes out to be pi square by 12 plus summation of an is 1 by n square cos nx and bn is 0. So no other extra terms, right? So this way you can get the Fourier series for the given function. Let's have another example. So here again Fourier expansion is asked over the interval 0 to 2 pi. So this is a full range expansion, right? So we will write first Fourier series that will involve a0, an and bn. We will quickly we will find out the value of a0. a0 is 1 by pi and then integration over we will write the limits of this interval as integration, right? So it is 0 to 2 pi f of x dx. Then again we will substituting f of x is x, integrating this, integration of x is x square by 2 and substituting the limits. Simplifying you will get a0 as 2 pi. Okay, then next we will have an is 1 by pi integral to 0 to 2 pi f of x into what we will have? See, an is in multiplication with cos nx. So here we will have cos nx. Okay, then substituting f of x as x. Now here you can apply simple successive integration by parts, or as one of the term in the product is a algebraic term, so you can very well apply the successive integration by parts. So here I am applying Bernoulli formula, that is successive integration by parts. So first function, then integration of second function minus derivative of previous first term into integration of previous second term. Okay, and then applying the limits. So what we will find here? So after applying the limits you will get such type of terms. Okay, sine of 2n pi is always 0, sine of n pi is always 0, right? So this term vanishes. Now we will have the term or the value because of this. So again cos of 2n pi. What is cos of 2n pi? That is minus 1 raised to power 2n. Okay, so what is that? That is nothing but 1. So we will have 1 minus 1, that is equal to what? 0. You can verify very well the values. Okay, now so we have an as 0. On the similar line we will find out bn also. So here 1 by pi integral 0 to 2 pi f of x sin nx. Then substituting f of x, that is x, over the given interval 0 to 2 pi f of x is x. Then again applying successive integration by parts. Okay, and then applying the limit, put x as 2 pi first. So you will have 2 pi n. Then sine of 2n pi as well as sine 0 is 0. So that's why I am having all the other terms 0. Right. So we have this as minus 2 pi cos 2n pi. Now there should be one more term that is respective to the lower limit, but it will not exist because when we put lower limit, so this x becomes 0. So entire term reduces to 0. So we will have only one non-vanishing term, that is the first term obtained for the upper limit 2 pi. All other terms vanishes. Okay. So substituting all the values, again minus 1 raised to power according to the formula, we will have 2n, right, cos of n pi. In place of n pi, n, what we have 2, so we will write 2n. Okay, so minus 1 raised to power 2n, again minus 1 raised to power 2n becomes the even number, right, as I told you, n is taking the value 1 2 3 4, so 2n will becomes 2 4 6, that is even, and even power of minus 1 is always 1. So it is minus 2 by n. So bn is minus 2 by n. Substituting the value of a0, an and bn, we will have Fourier expansion for f of x, which is x, as pi by 2. The value of a0 is nothing but, in our case, 2 by pi. So pi by 2 will come out to be pi. 2 will get cancelled. Then plus bn. So I will take minus sign outside. This is bn. Summation runs from n equal to 1 to infinity sin nx, whereas an we got the value as 0. So there will not be any term of cos nx. So in this way one can get easily, just following the steps properly and having the knowledge of integration, the Fourier series expansion for any function. Okay, let's have what will be the next possibilities. So here find Fourier series expansion of f of x is equal to x in the intervals. Just now we have evaluated Fourier series expansion of f of x in the interval 0 to 2 pi, right? But here also this the interval of length 2 pi, but the interval is of the form minus pi to pi, that is minus a to a. So always remember, whenever we have interval of the form minus a to a, we will first look for whether function is even or odd, so that we can reduce the number of calculation, right? So let us check whether this function is even or odd, right? So f of x is x given as, if we replace f of here in f of x by minus x, what we will find? We will get f of minus x is equal to minus of f of x. So this is nothing but a odd function, and in odd function we know that a0 and an is 0 for all n, whereas we will have only the term of the bn. Therefore Fourier series is given by f of x is equal to summation or n equal to 1 to infinity of bn sin nx. So let's find out bn. So as this function comes out to be the odd function, so that's why we will have the possibility for evaluation of Fourier series for a odd and even function. So over there you will find it will the interval, the limits of the integration will not be this entire limit. So minus pi to pi will become, according to the formula of definite integral, it will become 2 times 0 to a, right? So here a is nothing but pi. So 1 by pi will become 2 times integral 0 to pi. So this change one should note, one should remember, whenever we have the function as a even and odd and integral is of the form minus a to a, so there is a change in the formula. It is 2 by L, whatever value of L is here, and integral 0 to L, right? F of x sin nx. Then substituting f of x as x and simplifying the way we have done earlier, that is successive integration by parts and substituting the values. So what we need here, cos of n pi, the value of cos n pi is minus 1 raised to n. In the previous video lecture I have told you how to obtain the generalized value, right, how to apply the formula. So using that, as we know, cos n pi is minus 1 raised to power n, so apply that, you will get the value of bn in this manner. So after getting this value, let's quickly find out this, substitute this in equation number 1. So that's why the required Fourier series is this. So note here, this is to be done only when we have the interval of the form minus a to a or minus l to l, right? Okay, let's have the next example. So find Fourier series expansion of f of x is equal to x square. Again interval is minus pi to pi, so we'll check this function for even and odd. So let us replace x by minus x. So what we find, minus of x whole square. Minus of x whole square will come out to be x square. Okay, and that is f of x. So therefore function is even. As function is even, so therefore bn is 0. There will not be any term of sign. Okay, for all n. So therefore Fourier series will completely contain the constant term as well as the cosine term. Right, so that's why a0 by 2 plus summation n equal to 1 to infinity an cos nx gives us the Fourier series, where we will have to find out a0. a0 is, again as I told you, here it should be 2 by pi. Right, integral 0 to pi f of x dx, substituting f of x, integrating, simplifying. So we will get a0. On the similar line, we will find out an, that is 2 by pi integral 0 to pi f of x cos nx dx. Substituting again f of x as x square and then integrating this term by successive integration by parts. See here, in most of the example, or we can say in all the example almost, we will have to apply the successive integration by parts. Okay, because many times we find the function is algebraic terms. Okay, along with the cosine functions. So after integration, applying the limits and simplifying, you will come across the value of an as 4 times minus 1 raised to power n upon n square. See here, the sine functions, when we will apply the limit as pi, the sine n pi is 0, sine 0 is also 0. So first and third term reduces to 0, we will get the value only because of the second term. Again here we will have the value for upper limit only, whereas for lower limit this becomes 0, right? When we put x as 0, this becomes 0. So value is obtained because of the second term and for upper limit only, whereas rest of the values will vanishes. Right? Substituting these values in this formula 1, equation 1, we will get the required Fourier series expansion. So these are the set of examples which we have discussed for the full range expansion. Right, we will have the few more important example in a generalized intervals. Here, see here, we have considered the interval as 0 to 2 pi only. In the next video lecture, we will see what will be the Fourier series expansion, obviously full range in a general interval. Till then, keep watching, keep learning. Thank you all for watching the video.